Welcome everyone. Jeff Jensen, Director of Community Programs here with Trees Forever. We have a fantastic webinar for you all today. Phil Kerr is going to join us here. He is a quaternary geologist with the Iowa Geological Survey, and he's going to be talking about the last glacier in Iowa. A fascinating topic. I know you're all going to get lots of good information out of it. Reminder to connect with us on Facebook. We have this Stewards of the Beautiful Land Facebook group, and so you feel free to post pictures. We're coming to the end of the season here, but we still have things blooming, that is for sure. But we're going to have some stuff that we'll be posting here shortly. It's been a while, but check that out. And then just recently, very recently, we have this webinar. I don't even think it's on our events page yet, but we're going to have a webinar with Gina Bulow, our Trees Forever field coordinator based out of Ankeny, and she's going to do one on spooky nature. And so we're really excited about this one. Save the date, look back on our events calendar to get registered. That should be going live here shortly, but that's going to be a lot of fun, and can't wait to see what Gina has for us in regards to spooky nature. Okay, I want to mention a little bit of advocacy. So if you're not familiar, the world belongs to those who show up. And every 2 years, we have REAP assemblies. Now, REAP stands for Resource Enhancement and Protection. And these are funds that really are used in a number of different ways across our counties and in our cities. In fact, some of our Stewards of the Beautiful Land work is funded through some REAP funds. And so we have these assemblies. A few of them have already taken place. A lot of them are coming up in October here. And just want to let folks know that this is an opportunity because it's all of Iowa. All of Iowa is broken up into these different regions, and these REAP assemblies will happen in these various cities, as you can see, ranging from Marshalltown and Ottumwa, which have already happened, to those that are coming up here in Spencer, Des Moines, Mason City, Chariton, Afton, and so on. But this is where citizens and county elected officials, city folks, they can come to these assemblies. And one of the things I like to highlight is the fact that you can look on the list of funded projects, and every single dime that comes into the REAP pie, so to speak, that gets distributed between counties and cities and organizations, you can see where all of those dollars went. So you can see what was built or used in your county, and it's so accountable. And it's one of the most fantastic things about these REAP assemblies is it's an opportunity for folks to see for themselves where some of these dollars are going. And then, of course, the need for these different projects. So REAP assemblies are open to the public. The public is encouraged to attend. I would encourage all of you to attend if it's available in your particular area. Again, more information can be found on the Iowa DNR website, REAP, R-E-A-P. So really excited to let folks know about that.
There we go. Hello, my name is Phil Kerr. I work for the Iowa Geological Survey, and that's located in Iowa City at the University of Iowa. So if you've ever been to the campus there, I'm in Trowbridge Hall. I have the penthouse suite, but this is not it. I had to actually bike home because the software wasn't installed. So if I look a little sweaty, it's because I just got off my bike, not because I'm super nervous to talk about the Des Moines Lobe. So I'm a glacial geologist, and I do a lot of mapping around the state. I've mapped in Floyd, Mitchell, Chickasaw, Howard, Benton, and now I'm in Muscatine County. So if any of you know the landscape down there, it's pretty wild. But anyway, this will be talking about the glacial topography in central Iowa. So I'm going to start off showing how the ice sheet how ice sheets work, and then we'll talk more about the details in Iowa. So one thing I love showing at the start of these presentations is the Midwest. And I always take a grudge when people say that the Midwest is flat and boring, because they only say that with a human perspective. If you look at the Midwest from a large scale far away, you can see all these trends and patterns that you can't really notice with your eye on the ground. So there's all of these what look like smears coming from Minnesota and through the Great Lakes, and those are glacial advances from the north. So ice comes into Iowa basically from the north, and then also the ice descends throughout the Great Lakes over time. But we're going to talk more about central Iowa here. So Iowa in particular is pretty astonishing because it has this modern advance of the Des Moines Lobe, but it also has older advances that are at the surface. So I'm currently mapping down here where there's an Illinoisan margin that may have pushed the Mississippi River around 130,000 years ago. So what is Iowa? What's at the surface in Iowa? Well, there's a lot of glacial sediment. In some areas, it can be up to 300 feet thick, sometimes even 4 or 5 in western Iowa. It's pretty astonishing. And the main body of the main unit deposited by glaciers is called till. Some people, or it's been called drift in the past. It's not completely accurate, but it's a glacial diamicton. So that's a mixture of clay, silt, sand, all of these different materials with some boulders as well. And that underlies a lot of Iowa. So if you have ever dug a hole more than 10 to 20 feet in most areas, you'll find what people call blue clay. And that's the material deposited under an ice sheet. And in Iowa, we have some units. So I'm going to tell you these now because this is the modern stratigraphy. And I don't want you to get lost and mired down in the older stuff, which I'm going to talk about in a little bit. So this is from Alden Quarry under the Des Moines Lobe. So that's the sediment right here at the top. So the material right here was deposited by the last ice sheet in Iowa. And then that actually buries some windblown sediment, which is pretty astonishing because this ice sheet was hundreds of feet thick, yet didn't erode this dust. It's pretty phenomenal. And then that dust sits on older glacial advances all the way down to pre-Illinoisan, which is maybe 500,000 years old, and that sits on bedrock. So we'll get more into these units in a little bit. In the Midwest, though, Iowa sits in a very unique position. It actually is covered mainly by these older ice advances, so the pre-Illinoisan. So we can see the dark blue here is the most recent. So that covers most of Minnesota, most of Wisconsin, and parts of Illinois. And then we have this middle Wisconsin advance, which I'll talk about for a little bit. This is a new discovery made by the Iowa Geological Survey over the last couple decades. And this is an advance that is not well known because it looks a little bit like the late Wisconsin, but somewhat like the pre-Illinoisan before it. But we also have Illinoisan advances from the east, so where I'm mapping now in Muscatine County. And ice down there came in from the Great Lakes. So that would have dramatically affected the river systems. And I'll talk to you all about how the Des Moines Lobe did that so you can get an idea of it. But most of Iowa is covered by this older pre-Illinoisan sediment. So what makes Iowa unique is we have all of these important glacial episodes, and it makes it so that if you want to talk about how ice sheets grow and stop in North America, Iowa is a fantastic place to do that. That's why I look so beaming and happy whenever I go to work in the morning, or a little sleepy, depending on the day. The other thing to note, though, is that there's this area in southwest Wisconsin which is truly unglaciated. All of Iowa has been covered by ice, even though some people call northeast Iowa the driftless region. They get around that by saying, oh, well, it wasn't glaciated by the last ice sheets, but by calling it driftless, that implies that it's never been glaciated, but it has. I just went out last weekend with a professor from UNI and found some till in Jackson County, which is supposed to be driftless, but you know, there's names, there's accuracy. We'll talk about that later. So maybe another talk sometime in the future, I can talk about that with this group. So anyway, the important thing to note, though, is that all of the Quaternary is the Quaternary extends 2.58 million years into the past. And when you think about this like a book, you know, these last ice sheets, these last glaciations and interglacials only represent 5% of the time period. So when we talk about how ice grows and melts, we really need to think about the pre-Illinoian. So that's something that Iowa has that is really inaccessible in other regions. So our pre-Illinoian stratigraphy updated uses a couple different ways to get at it. And the main one that we use is ash layers. So Yellowstone erupted, deposited sheets of ash in the Midwest, and we can date those and see the differences between the ash layers to get stratigraphy. And we can also use the magnetic polarity of the tills, because as the ice deposits them, the grains orient with the magnetic grains orient with the magnetic field, and then over time the tills dry out, so it's locked in place. And some of the older tills actually have a reverse polarity, so we can use that to determine the timing of these things. So if it's older than 800,000 years ago, it'll have a reverse polarity signature. All right, so let's get into some glacial history, some older tills, some ideas, and we'll talk about how ice sheets work and then how the stratigraphy got made. Because, you know, the story of ice in Iowa has been evolving ever since the late 18th century, which is when this picture is from. So part one we're going to talk about is, what is a glacier and what do they do? So glacier, if you just break it down into the simplest idea about what is ice and what is a glacier, it's ice that flows due to internal deformation. So if you get out a pack of ice, like a big one, fill a igloo cooler with one, or a Yeti, if you do that, and freeze it solid, that block of ice that you dump out is not a glacier because it doesn't move due to internal deformation. What causes that is you stack up so much ice that it flows out like putty. So imagine you stack a bunch of jelly on a counter and eventually it will ooze out. Ice does that, but on a much larger scale. So it has to be tens to hundreds of feet thick to do that. And it's that thick because it is the accumulation of snow year after year. So the reason that there's no ice in North America now is because the snowfall in Canada doesn't survive through the summertime. If it did, that would change the reflectivity of Canada and promote cooling, because it would reflect light off, and then that would help start this cycle where you can pile more snow on again and again and again, and eventually that snow, those little snowflakes, change and condense, so they go from snow and then they start to get crushed by their own weight, and so the porosity, the space in between them, becomes smaller, and then you can get granular ice. And then firn is when it's almost to the density of glacial ice, and there's still connectivity to the atmosphere. But after you get so much depositing, you close those air bubbles off, and that's when you have glacial ice. And so if you look at ice core records from Antarctica, we can actually sample those air bubbles and determine what the atmosphere was like in the past, because we can count back summer and winter seasons, because there are layers in this material. So here you can see a photo where there's a darker layer, which is the summertime when snow will melt, and each snow crystal has a little bit of dust in it, because that's what it nucleates along. So if you melt them, you'll get a dark layer, and then the clean white snow is a lighter layer in the ice sheet. So those can be counted, which is pretty wild. So the idea about how these ice sheets move and melt, though, is an important thing to get across. So if you think about them kind of like this wedge, you have an area where snow is building, so that thickens things. And then once they get thick enough, they flow down into either lower elevations, or in our case, lower latitudes, where there is more solar energy, and then those will melt. And so that will then draw more material down, because it's like a stopgap. Once you melt back some of the ice, then there's less pressure holding the ice upstream. So then you'll get this runaway feature, unless there's balancing between deposition and melting. So there's two main types of glaciers. Those that are constrained by topography, alpine, and those that basically aren't, and that's continental. So almost all of the ice sheets that are in existence, besides like two, are alpine. So the two that aren't, that are continental right now, are the Greenland and Antarctic ice sheets. So North America had a continental scale, but it's completely gone. Europe did as well, but those started in mountainous regions in part. So they behave a little dissimilarly. But how do these ice sheets move? And because they're giant blocks of ice, they have properties that are similar regardless of the topography. And it depends on what they are moving over. So if you have a really cold glacier where there's no slip on the base, and that slip is due to water melting, getting down to the base, maybe there's some softer sediment. But if you can imagine like a hard rock like granite, you're not going to be easy. It's not going to be easy to slide over that. So if there is that hard rock, the only way that these ice sheets move is through internal deformation or due to their own weight. And so that's why ice in Antarctica moves generally slower than ice is thought to move in North America, because some of these ice sheets were temperate because they got down to Iowa and they had these beds where the ice, due to the force, could like push the ice in front of it further because it was like on clay or water or something like that. But ice moves like a river. If you've seen diagrams of water flowing in the channels, there's the most friction on the boundaries. So the fastest that the water, and in this case, ice is going to move, is right in the middle, the farthest away from the edge as you will. And so in mountains, what that does is it creates these flow lines, but in continental scale, it creates ice slopes where the center goes the furthest and then the boundaries slow down, giving you this tongue shape. And we'll see that when we look at the Des Moines Lobe. An important thing to get across as well is that ice moves even if the ice sheet boundary is retreating, because it's moving and melting. So it's like a conveyor belt that you're pulling back. So you can see here this rock in example A, it's still moving down slope even though the ice is retreating, because the ice has this internal mechanism but is melting. It's pretty weird to think about. And as these ice sheets move, as the ice moves, it grounds up stuff underneath it. So one thing that this ice has a lot of mass. Like imagine a stack of ice 200 feet to 2,000 feet. In some case, some of the ice in Canada was as high as the Rocky Mountains, so about 10 to 14,000 feet, which is nuts. All that force, and then adding into the movement, will then deform and strip the sediment underneath it. And the ice is soft, but what it'll do, it'll grab on to rocks and then move them over the material beneath them. And so if you have a ridge, like a little hump, you'll abrade one side and then pull material off, because water will get down into these cracks due to the pressure of the ice going up, and then it'll melt and wedge those joints apart. And that's called glacial plucking. So the other way it erodes and deposits is, or the other way, where it deposits the sediment is either at the base, or in some cases you can actually get crevasses due to the force and strain moving material up onto the top of the ice. And this is more common in alpine situations, as you can imagine. You can also get material falling from the valley walls that are at a higher elevation. And then the main way in Iowa that sediment is deposited is underneath the ice sheet. So as it goes, the ice will melt and it will deposit some of these materials as glacial till or blue clay. It's way more complicated. You can get into this for an entire career and then some. But in general, there's till that's deposited under the ice sheet, and then there's stuff that melts out as the ice retreats. And here you can see alpine glaciers coming together, and in between, you have this really fantastic lateral moraine between them, and that's going to be visible when these ice sheets retreat, which sadly most ice sheets in the world are right now. So let's ask a question to ourselves. What would this bad boy do, this alpine glacier, as it advances? So it'll take a landscape that looks potentially like this, and then over time, you'll have smoothing due to abrasion. So imagine if there's just a giant sand block, which is the ice holding the materials, that will then erode and carve the ice until it could potentially look like this. So this is from an alpine glacier in Peru. So pretty phenomenal. And the dips and troughs will then enhance themselves because there'll be more pressure in the basins and on the sides. And so you over deepen those. So one of the things, though, that glaciers also do is they'll erode their own material, so their own tills. And that way you can actually see evidence for multiple glaciations because you have what's called a disconformity. And that is this boundary in between where you have this original material, the blue clay, the till, deposited, and then over time it interacts with water, with air, and that oxidizes the sediment. It basically rusts it, and then you have a soil forming on top. But that represents a period when there wasn't deposition of till because it sat under the air. And then the material above it is the next till sheet, and that shows the same pattern of gray, unweathered, and then the orange on top. So that's evidence for multiple glaciations, which leads to stratigraphy. And don't worry, I'm not going to quiz you on this. This is extra credit if you want. But I want to get this across that some of these names that are used are not in use anymore, specifically Kansas and Nebraska. And we'll get to that towards the end of this section. So the first mention of glacial sediments in Iowa is attributed to D.D. Owen. And he started this trend where he describes erratics, so giant boulders found in Iowa on the uplands from rocks that are not present at the surface, specifically like granites, phyllites, all these metamorphic igneous rocks found in Canada and Minnesota. He described them as ice drifted by currents setting in from the north before the land emerged from the ocean. Well, I mean, yeah, but geology is way more, our ideas of geology are way more sophisticated than then. So we realized that it wasn't drifted rocks because these things are denser than water. It has to be something that can actually pick them up. And frozen water is great at that because the density and the energy involved in it moving can transport these materials vast distances. So Louis Agassiz, supposed to be the father of glaciology, had or presented the concept of older glaciations because he found these erratics and then traced them back up to the area where they were originally. And they were much further than they could be if they were just to slide downhill. And then seeing, oh, there's still ice in the valleys up further from here. Maybe these ice sheets were much more extensive at one time. Well, in 1868, a researcher called Worthen showed that there were buried soils between tills. So what that means is there had to be multiple times for ice advance. And here's a close-up of one of those disconformities. And so this is the start of stratigraphy. Here's an actual soil. So you can see the soil forming in one till. Look how black and black that is, just like today's soil. And then there's an ice sheet that rode right over it. So when these were found, people started to correlate them based on the shape of the landscape and what looked like a glacial advance. So they scaled up these alpine tongues to give us the Des Moines Lobe, which was originally called the East Wisconsin Advance, which I think should be the West Wisconsin, but you know, who am I to argue with T.C. Chamberlain? And so this starts this pageantry of nomenclature where we just name things, do some research, refine boundaries, refine names. And it starts with those two and then adds in Kansan. So the East Iowa is basically the Des Moines Lobe. East Wisconsin is Des Moines Lobe, and the East Iowan is a topic of another seminar. So if you want to see that, look through Trees Forever's YouTube page. So these advances changed, and then afterwards they added material in between them, so paleosols. 1896, they added the Illinoisan, which I'm currently mapping, and they got it mostly right. And then the state geologist Calvin said, our knowledge of Pleistocene geology has moved with tremendous strides during the last 2 years. Well, yeah, if you like double the amount of names of your glacial advances, that's a pretty big shift, especially, before television, phones, cars. So when they went out to do field work, they used horses and birch bark canoes, which I think is pretty wild. In 1899, Leverett added in the Sangamon between the Illinoisan and Kansan. And then Shimmick changed the name of the Albertan, which was underneath the Kansan, to Nebraskan. And that basically held through until the 1960s for the most part. So there's only been one major change in that period until the 70s. And that was done by one Robert Ruey, who said, this Iowan lobe concept doesn't really work. And again, see the last presentation to get more on that. So in the 70s and the 80s, that's where things stood. However, these older advances came into question due to the work of John Bolstorff and finding more of these ash layers. So the demise of the Kansan and Nebraskan is due to more drilling and matching outcrops, especially with ash layers in between. So it was thought at one time that that was a single ash layer. However, Bolstorff showed that there was multiple, there was different ashes through fission track dating, and then eventually traced the geochemistry back to 3 different eruptions in Yellowstone. So what was once the Kansan and Nebraskan, and then maybe an older till, is actually multiple tills separated by different ash layers. And ever since then, we've called these the pre-Illinoisan advances. So these ashes came from Yellowstone. So you can envision why you would see those, because those were major eruptions. However, they didn't get into eastern Iowa. So there's a bit of a difference between the stratigraphy on the east and the west side of the state. So we're not going to get into it too much. But once again, here's that same figure, and you can see, as shown from before, but we still use the ash layers to classify these tills. So the eastern, or the left side, is from Iowa, and then the figure on the right by is from Missouri, so they're a little different too. So let's talk about the non-pre-Illinoisan. So let's go to middle Wisconsin. And so what was discovered at that Alden quarry was there was the late Wisconsin advance, there was something in between, and then there was another till above this massive paleosol. And radiocarbon dates in the 80s show that, oh, this is actually not pre-Illinoisan. It's not Illinoisan, it falls within the Wisconsin, but it's not the late Wisconsin, which is starts about 29,000 years ago. It's middle Wisconsin. And so the Iowa Geological Survey has collected more radiocarbon samples to show that that's true. So let's talk about radiocarbon samples for a second. Well, what you do is you find organic material and you use the ratio between radioactive isotopes and the stable. So the radioactive isotopes have a half-life about 5,730 years or so. And you can calculate the difference between what you would expect there to be in the atmosphere at any time and how much is left from that. And those half-lives will tell you the amount of time it takes to get to that. So the problem with that is we're just getting to the edge of these values. However, new technology has allowed us to get to such small percentages that we can get back almost 8 half-lives now at 50,000 years. After that, there's noise, there's random counts and materials that will sometimes give false readings. So we cut it off at about 50,000. What else is there? So what is buried generally is wood or peat. Sometimes soil is used, but soil is tricky because it's not one thing. It represents when the soil is forming. So it's not like one age, like when the ice pushed over a tree, which is my favorite thing to date. And that's a piece of wood in that glacial till. So we have a bunch of ages from across the state showing that that ice was in Iowa before the Des Moines Lobe, and we're calling this the Osage Lobe now. So these potential older margins, the Osage Lobe came down on the east to about Osage in Mitchell County, and then potentially as far south as the Algona moraine, so north of Boone, and it went across west, and Storm Lake is formed in part by this lobe as well. And then the ice readvanced about 30,000 years, so it's the Lehigh phase of the Osage Lobe. And then the Des Moines Lobe came down much, much later. And so I'll talk to you about that. And here we are. This is the bread and butter. This is what you all came for, the Des Moines Lobe, the last advance into the state. So the Des Moines Lobe is pretty special. It's a really wacky lobe in comparison to almost every other lobe to the east. Its brother, the James Lobe, I guess you could call it, behaves similarly. They're very fast advances of thin ice, and they're thought to come much later than the other ice sheets, and we'll show that that's actually the case. So where did this ice come from? Well, the ice came from basically Manitoba. So there's a trough formed by repeated glaciations in the area, and ice descended down that because it's a smooth, flat, focused area where ice can just have a release valve to the south. And that material can be anywhere from, here it is, it's only 2 meters thick at the Alden Quarry, to up to 6 feet, 6 to 10 feet. And then it can be up to 50 to 60 feet in some areas. So it's pretty thin deposits. And the Des Moines Lobe till plane is pretty distinct in Iowa. And here you can see the elevation of the landscape. So here's Des Moines on the southern part. You can always tell Polk County because of the weird little kind of chin beard, if you want to call it, formed by the Des Moines River. And this Des Moines Lobe is loaded with moraines. So this is something that's uncommon to ice in the east, is these really distinct, smaller recessional moraines. So these, next slide here. Oh, yeah, that's where I'm from. So I grew up in Marshall County. So not on the Des Moines Lobe. I'm not a Lobe baby. I'm a Southern Iowa drifter by definition. But, you know, driving to Ames, I drove across the Bemis Moraine right after State Center going on Highway 30. So these major moraines, though, are pretty obvious on the landscape. So you have the Bemis, which is the terminal moraine of the Des Moines Lobe. And then after that, you have the Altamont 1 and 2. So ice advances and retreats, and whenever it advances and stops, you get a moraine. It's like a bulldozer and conveyor belt stopping in the same place. So you get a little bit of a push up, and then the ice will bring those materials down and stack them up as well. And then the last advance in Iowa is the Algona moraine, and this is a serious moraine. In some areas, it can be 100 feet above the rest of the landscape. And in northern Iowa, 100 feet is basically, you know, that's the highest thing around. The other thing that these moraines do is they block water as the ice sheet melts, and these can form glacial lakes. So here's a map of the soil series that I've coated to parent materials, and this blue color represents lacustrine sediments, so silts and clays laid down in still water. And so as ice was retreating, the moraines block the water until a later time when they burst through. And this is very interesting because it's not everywhere, it's only in certain parts. So that can tell us the behavior of the ice sheet in conjunction with radiocarbon ages. So here's some new data that I threw together for you all. So this is the first time it's been presented. And what I'm trying to show is the behavior of the ice using these radiocarbon ages. So it's a little complex, but I'll walk you through it. So all of these organic sediments that are associated with the Des Moines Lobe, they can fall into basically two categories, where they found above the glacial sediment or below, or sometimes within. So there's a third one, but that's a little sneaky. And so if you actually refine it even more, the ice can have re-advances, and you can find sediment with evidence of that, because as ice retreats, it's warm in Iowa during this time relative to areas around and 10,000 years before this. So trees will grow. So if ice doesn't occupy an area for a few hundred years, there will be trees and vegetation growing. And if the ice re-advances, it'll grind those up. So how this figure works is up at the top is the latitude from south on the right-hand side to north on the right. So the Iowa-Minnesota border is represented by this black line. And then time, the years before present, is represented on the X or the Y-axis of the chart. So areas that don't have blue are ice-free. Areas that have blue on them are covered by the ice sheet. So from about ice advanced into Iowa potentially about 7,500 years ago, and then was hanging out in the northern parts until it got down to Hardin County at 16.5, and then just shot down to Des Moines in less than 500 years after that. And so the ages here, the blue ones, these light blue, are from wood in the till. So that's basically material that the ice picked up. And some of these older ages are peat, so there was a bog in the area. So those wood had been chilling in that environment for a while, and then they're older than when the ice actually got. But some of these are from trees pushed over by the ice, and you can see snarls of them, and it's pretty wild. So ages show that the ice was got to Des Moines about 15.8 thousand years ago. Oh, and here are the different timing of the moraines. So they match with the topography of the Bemis and the Altamontes and the Algonas. There we go. So the Altamont re-advance buried a piece of wood shown right here, and then rapidly retreated because there's ages from a bog, the bottom of the bog, on top of the glacial till from about that are about 15.2 thousand years ago. So these are thin ice sheet. This is a thin, fast ice sheet that comes in, melts, and then re-advances from ice behavior of ice. And the Algona, the last advance was a little after 15,000 years, so maybe 14.8 thousand years ago. And some of these ages might not match with older literature, and that's due to the calibration of radiocarbon ages. So that's a pretty in-depth topic, but the basic idea is that the values of radiogenic carbon in the atmosphere vary from year to year because they're generated via solar or cosmogenic rays hitting atoms, breaking them apart, and the fluctuation isn't always going to be, the generation of those isn't always going to be the same rate. So we calibrate those using other age techniques to string together what was going on each year. And so it's been a long project. But what it lets us do is to represent more accurate ages rather than just going on ages generated by half-lives. So these are the ages for the advanced Des Moines Lobe. The Iowa Geological Survey is going to be doing more work on this, so learn these ones. But the big thing is that the Des Moines Lobe reached its terminus at 16,000 years ago, whereas other ice sheets to the east were much later or much earlier. Like the one in Illinois, I think it was about 23,000 years ago, whereas the ice reached its maximum in New England shortly after 30,000 years ago. So that's 10 to 15,000 years before the Des Moines Lobe. So it's really late to class, you could say. It's running in, slipping on water and sediment and sliding in. So the one thing that it does, you can see all of these major moraines shown as the big arrows, but there's also these smaller recessional moraines. So it shows that the behavior of the ice was advancing, retreating, and re-advancing, kind of in the stuttering method. And what these moraines did, though, was they changed the behavior of rivers. And so we're going to talk about the Iowa and Cedar rivers, which are shown here. So the orange lines are where the Cedar Valley is now, and the blue arrows point to the Iowa. So here's where the Iowa is now. And you can see how it snakes up to the north. But if you look closely at the landscape, you can see it changes its orientation at moraines. So these moraines would have been there and would have been just a wall that the river had to eventually break through, or they were formed at the same time as the moraines due to tunnel valleys. And so it really depends on what was going on of how these rivers would have reacted to the ice. So here's my personal hypothesis on the area. The Cedar River actually occupied, was occupying most of that or the upper part of that Iowa watershed. And we can see that because of the landforms. So look at this channel here. It looks like the Cedar wants to really occupy this valley. So why would the Iowa River pirate it? Well, let's look back to this map, the one showing where the glacial lakes are. Well, look at that. There's a glacial lake sitting up here. So maybe when that water melted, it overrode the landscape that was set behind one of these moraines, which would have been flat, and then it just happened to go further south than the Cedar. And that's what we see by looking at that landscape in question. So this is the area where that diversion, that pirating happened. So the Cedar River would have flown or would have been draining this way, and then eventually that was blocked off by this moraine. The channel was buried by glacial till, so there's actually buried sand and gravel here. And so once that lake drained, it went through and then hit this other moraine and flowed into the Iowa basin. So these rivers are pushed around by ice sheets because, well, of course they were. They're massive and they bring their own water to the party. So those little crinkles that you saw on the landscape are washboard moraines, and they're also called crevasse squeeze ridges. And work by Neil Iverson, the students show that they form when you have ice advancing and it slows down due to some reconfiguration. And then if it gets kind of hit from behind, so rear-ended, it'll squeeze those ridges or the crevasses that form will squeeze up and kind of pinch the material beneath them. And so it's a response that can show you what the previous material or previous landscape was, because the ice will flow quicker over flat clay-rich sediment. But if it's over sand and gravel, it will actually drain the water underneath the ice sheet, so it'll move slower. So this is Ames, and you can see a really interesting feature right here that we'll talk about in a second here. So these washboard moraines are pretty common, but what is more interesting, or just as interesting, is that bend right north of Ames. And so that bend in I think that's the North Skunk River, or it's some tributary of the Skunk River, it might be the Skunk proper. That is the result of a glacial lake forming there. And so that water built up and then shot down once it was released, once it burst through the boundary. And in that little bend, there's actually shallow bedrock. So it hit the bedrock, was diverted around until it's kind of scooted around down south. And the consequence of this is actually seen past the Des Moines Lobe in this track. So the Skunk River comes down and then it drains, and you get these giant meanders from this big meltwater event. So this might have happened over the course of a few days, a few weeks, but it wasn't a long-term event. It wasn't slowly draining. It was a burst, and that shows in the river south of that. So these big meanders are not common in other rivers, and this is especially interesting because this shows that the Skunk rivers were not drained extensively, or didn't drain ice sheets extensively before. So overall, what the lobe to landscape pattern looks like is shown here. So this is step one. We firm the terminal moraine because most things before that aren't as important as what happens as the ice retreats, because that's the landscape that will likely be left after glaciation. So you have the terminal moraines, and then you add in these smaller moraines. And if you look at meltwater flow paths, you can see a trend. So these are areas where it's poorly drained, and there's channels that are abandoned, even though they're sometimes hundreds of feet wide. Those flow paths are pretty ugly on here because there's so many of them. But the consequence is that these moraines are hills, and those hills will control where water goes. And the ice sheet also controls where that goes, because if the ice sheet stops, there'll be water flowing off the snout, and that will set up rivers as well. So Iowa's drainage patterns are set up by ice, and they're not dendritic necessarily, they're more trellised. So you can see here where ice set up moraines, which then causes these tributary rivers to come in at right angles. And that is something that is indicative of a glacial landscape, especially one formed on older till sheets, because bedrock can't affect these. And the resulting topography, like this shown in Webster County, is a consequence of that. So yeah, Webster County is pretty flat. So the highest area in the county is this moraine, and it's about 1,215 feet high. And the lowest spot is in the very southeasternmost part of the river valley. However, that is due to later fluvial incision. The lowest part on the upland landscape is right about in here, and that's 1,800 or 1,080 feet. So there's, that should say less than 200 feet of elevation change on the uplands of Webster County. So the Des Moines Lobe flattened the landscape out, and that will affect drainage, which gives us problems that, or causes the landscape to form certain things that humans interact with. So if we look at this area right in here and blow it up, you can see these are the meltwater flow paths. These valleys have absolutely nothing draining in them except for channelization. So humans want to speed up the water, and they put channels to drain this landscape in. Elsewise, these would have been marshes. And that's what we see in certain parts of Iowa, is these depressions form wetlands. So the Des Moines Lobe would have been one big marsh, and it would have been main majority prairie, and it would have been windy too. So all of these things are the legacy of the ice sheet. And the modern effects, how that affects our behavior on the landscape now, is mainly seen in drainage because of this flat topography, because of this short interval for ice retreating and then the landscape incising down to. Water doesn't move off this surface very well. And so people have installed egg drains. So fields, you'll see these strips if some of you aren't familiar, and that's where farmers insert pipes, usually plastic, into their fields every, I think, 30 feet or something, 30 to 50 feet. And these tiles are perforated, so water will move down into those and then drain out. And Iowa, because of this, is the most modified landscape on the face of the earth. If you go out to central Iowa, there's human activity underground everywhere, and there's multiple iterations of those. So the original field tiles were actually clay, and you can see them sometimes poking out of drainages. So some of these fields have been tiled 2 or 3 times, depending on who owns them and how the system holds up. So if you look at all of these other factors for, where's tile drainage common, where's cropland, where's the slope, where's it flat, where's the soil data say that the surface is poorly drained? Well, let me tell you, there's a pretty big correlation with the last glacial boundary. So this margin right here, where the ice sheet stopped anywhere from 29 to 16,000 years ago, flattened the landscape, which then allowed for certain factors that are productive for farming, specifically like rich organic topsoil. And so that boundary, which is just copied and pasted over, is very clear in all these other maps. So once you start seeing maps of the United States, a lot of things are caused by glaciation. I mean, why not? They're giant ice sheets that flatten out the landscape, change the topography, and the result is that Iowa has some pretty rich farmland. So the conclusions of this talk, which you should just take away with you, put in your pocket and think about later, there were a lot of glaciations in Iowa. It's been covered by ice anywhere from 12 to 20 to 30 times, depending on who's making that guess. We have direct evidence for 12 times, but there's likely more that we're missing because of the glacial erosion. The most recent event, though, was the Lake Wisconsin Des Moines Lobe, which reached its terminus around 16,000 years ago, 1400 BCE, if that's how you want to think about it. But I used the years before present. And as that lobe advanced, it flattened the topography, rearranged rivers, and the consequence is that landscape has pretty high yields. So I'm not going to get into anything more than that because that's out of my topic. So anyway, thank you for listening. And if you have any questions, I'll check the box and answer those. So let's see.
Thank you, Phil. Absolutely. That was a fantastic presentation. I've got the questions up and I'll type them in if I could, as best I can anyways, as you answer them. But one of the first questions here is, were the Loess Hills in Western Iowa built up before, during, or after the last glacier? Or all of the above?
Boy. You just had to ask that. It's actually really complicated because there's a really complex timing between glacial outwash, glaciation, and loess development. So that's something that I'm also interested in. And the Loess Hills are ages from those show that loess really started to pile on about 24,000 years ago. But what that means then is that there was something going on at that period that would be beneficial for loess accumulation. That could be that the climate changed, it got drier, it got windier, or the ice sheets like the James and Des Moines Lobe entered the Missouri Basin because these rivers, the Missouri River hasn't been in constant, it gets pushed around by the ice sheets as well. So the ages of loess in eastern Iowa are roughly about the same age. So it's a combination of those three things. And so that's why if you look at the timing of the Des Moines Lobe in Iowa, it doesn't show, it's much later than the loess. But that makes sense because your water goes much further than your ice sheet, so you can get water in your basin before your ice sheet shows up at your front door too.
Excellent, excellent. Thank you for that. Now, Gloria wants to have a presentation on the driftless zone, so we'll have to keep that in mind for the future. And I'll be sure to put a link when this is posted to that other one you did, the Iowan. That was a great presentation that a lot of folks commented on, and I think that's the one you referenced in your presentation a couple times. So
yeah,
we'll get that to folks too.
Yeah, I don't want to give that presentation again. It's a lot of work. No. Boy, it makes my head hurt.
We've got that one recorded and good to go. So some Iowa terrains are called driftless, and what does that really mean?
So we have this idea about what landscape is, and the way it's passed down is through word of mouth in a lot of areas. Like we have these man-made boundaries. Like what is Johnson County? What's Des Moines County? It has no basis in reality. They're just boundaries defined by humans. And so the driftless region has evolved of this topography. So it's not based on the presence of ice, it's based on the topographic effects of the development of the Mississippi River. So southwest Wisconsin is truly unglaciated. However, eastern Iowa, northeast Iowa, has been glaciated. I found till, I found erratics. AC Trowbridge has a publication called Drift in the Driftless Region, and that shows there's glacial sediments all the way up to the Mississippi River. So it's not that it wasn't glaciated, it's that the rivers up there, the upper Iowa, the Yellow, the Turkey River, drain right to the Mississippi River, so they incise down, whereas the Maquoketa, the Wapsipinicon, and the Cedar take a more circuitous route around and then have a flatter long slope profile. So that next talk will explain that. So I don't know when, sometime in the future, look for that.
We'll get it scheduled for sure, for sure. Uh, Phil, Maryland wants to know, how did the glaciers form all those lakes in Minnesota, 10,000 lakes, and not in Iowa?
That's a great question. So the answer to that actually is determined by which direction the ice flowed from. And so in Minnesota, the Minnesota stratigraphy is way more complicated. Actually, have the map of their state right here, and it's huge. They have all of these advances, retreats, readvances during the Lake Wisconsin, and they have multiple areas where the ice can come from. So it can come from the northwest, the north, the northeast, and almost the east. So that ice coming from Lake Superior would have been a much thicker lobe because it has to get into that lake, push the water out, and then come back out. And it's also riding over hard granites. And so what that does is it causes a different style of glaciation versus the Des Moines Lobe. And that thick, massive ice sheet, when it falls apart, you have these giant chunks of ice that could be hundreds of feet in diameter. And if the ice collapses and falls apart, you'll have these sitting on the landscape. And then the sediment from other ice and melting will form around them. And then when those lakes melt, you'll get kettle lakes. And so the boundary between western Minnesota and the lakes region is actually formed by the Des Moines Lobe because it came in on a very smooth bed, and when it fell apart, it wasn't thick enough to form these kettle lakes. At least that's how I interpret that boundary.
Well, let's actually, that's a great segue to a question by Chuck here, because he wants to know, could you share a bit on the formation of the Iowa Great Lakes and their association with the glacier?
Yeah. So I actually mapped Storm Lake last year, and that was pretty wild because the Des Moines Lobe, the lakes up there are not kettle lakes. They're from releases of meltwater. And mapping Storm Lake, there is a trend where there's likely superglacial lakes, so lakes on top of the ice sheet. And once you start forming those, the water will kind of carve out a valley or a basin on top of it. And so each year you fill this in. And then once the water gets warm enough, it can actually burrow through to the substrate underneath it or spill over the top and front. And that's how I think Storm Lake was formed as the ice reached its maximum extent in western Iowa. But the Great Lakes region is different because Storm Lake is like 8 feet deep on average. It's shallow. The Great Lakes region, Okoboji, Spirit Lake, those are super deep. And that must have been from a massive outburst of water that carved those out in areas that can be, I think, over 100 feet deep. But that water then reached the Little Sioux Valley and then just carved that valley out. And there's multiple stacks of sands and gravels that you can see in the Little Sioux River from that outburst.
That is phenomenal. Wow. Well, and I live here, Phil, in Kossuth County. Algona is our county seat, so I'm up here in the Algona portion of it, and I am reminded of the original land surveyors notes when they came across Iowa, and I am paraphrasing, but they wrote something akin to uninhabited swampland. So amazing that you said that whole thing would have just been a swamp. But
yeah.
Clear Lake. How about Clear Lake and the glacier and how that might have been affected by the formation?
I actually helped map Clear Lake too, and it looks like it's the same rough formation as Storm Lake, except Storm Lake is in front of the ice and Clear Lake is behind the margin. So I think it formed roughly the same way, where you have lakes forming on top of the ice as it retreats, and then that spills down where the ice is, the orientation shows it, or the orientation allows for that, and then it will carve out these depressions as it comes off like a waterfall, and then carves out a little bit of the lake, and then ice retreats more, carves out a smaller segment and smaller. And the question is then, like, and that kind of answers why, as you have these lakes, do they get smaller towards the ice sheet? And that's because of the changing of the lakes on top of the ice as it retreats. So yeah, water on the ice falling off in front of the ice sheet will give you those lakes if there's not subglacial drainage.
Excellent, excellent. Well, if anybody else has any questions, speak now or forever hold your peace.
I have a question. Someone asked, we have heard that Lake Superior prevented some ice from glaciating northeast Iowa, and asking if I agree with that. And I do in part because the orientation of the Lake Superior was due to the Mid-Continent Rift, which is this giant hole in North America. And as ice enters that, it will orient it with the rift, and that curves around and forces ice to go around southeast Minnesota, and then the Lake Michigan forms due to the Michigan Basin, and that orients the ice around as well. But the ice coming from the northwest, from Manitoba, actually will then, it comes from the north, and at one time it went more eastern and formed the Mississippi River and northeast Iowa. So there is indications that the Great Lakes did help orient ice around northeast Iowa for a period, but the ice from the other side, from the west, snuck in and glaciated it, probably early in the Quaternary.
Excellent. Is it true that the Iowa Capitol building is built on the Des Moines Lobe terminal moraine?
Yeah, it is built on the Bemis, so that's why it's up there. I just think calling it the Bemis Capitol just really doesn't have the same ring as what was it, Fort Raccoon, before they changed the name to the Monks.
Okay, interesting to learn about what created the Mississippi River, which is Iowa's eastern border and drains such a large area in the central U.S.
Oh boy, that's a really complicated question because
Another presentation.
oh no, well, this will be years in the making.
Okay, okay.
Well, the issue with the Mississippi is that it hasn't been in its modern configuration for every single segment changes. So from like Clinton to St. Louis 24 or 25,000 years ago, it likely it's shown to flow through Peoria, from Clinton to Peoria to St. Louis. And then the Lake Michigan lobe blocked it, formed a big lake there. That overspilled and into the modern segment that now goes past Muscatine, past Davenport. So it was blocked by ice. And that's why the Illinois River is abnormally large around Peoria. It's because that was the old Mississippi River. But then the Wisconsin River actually flowed the opposite way, potentially as young as 30,000 years ago. So the water north of Dubuque would have been flowing into the Green Bay, or Green Bay. So that's a topic that Eric Carson at the Wisconsin Survey has been working on, and it's really convincing data that he's been putting out.
Phenomenal. So interesting. This is really a pet topic of mine that I love, and so I can't thank you enough, Phil. We're going to wrap things up here, but we will invite Phil back in the future for another great presentation. He's got a lot of stuff to talk about. So thanks, everyone. Have a great day. This will be recorded, and we'll get it posted here to our YouTube page shortly. Thanks, everyone. Have a great day.
Thank you.